everyone. So we just left off talking about multi-mass systems, and I want to move on to something a little bit more unique about the multi-mass system. So what we did was pretty much a more basic setup. I could make it a little bit more difficult, adding in friction, but for the most part, the method doesn't change. However, now that we're moving on to the more complex setups, I need to talk about something called an Atwood machine. So an Atwood machine is actually a very unique type of multi-mass system. In it, you have two masses hanging from a string, and the string is wrapped over a pulley. Now, we're going to take the initial simpler case where the pulley is massless and frictionless. The reason why we're going to mention this and make note of this is because later on in the year, when we get to the rotation section near the end of this course, we're going to find out that when the pulley is not massless, when the pulley has friction, then what we end up having is a scenario where the tensions on the two ends are going to be different. In this case, this ideal case, if you will, where the pulley is massless and frictionless, this is going to allow us to make the statement that these tensions are equal. Basically through Newton's third law. And this makes it very similar to what we did previously. If you recall, in the previous case, we had two blocks touching each other, and then there was a contact force which was acting as the force interacting between them, causing them to move together. Here, that interactive contact force is now going to be replaced with a tension force. So that's going to be one slight difference between the Atwood machine and what we've been talking about before. Now they're not physically touching each other, but they are still interacting through the tension. So a very common question could be to find the acceleration of block M1. For the most part, this setup is actually a very simple one. Once I show you how the Atwood machine is set up, it ends up being very easy. There's really not much I can do to make this question tougher. Maybe instead of giving you an acceleration, I could have you find the acceleration using the kinematics equations, but that just makes the problem longer, not harder. Later on, we're going to talk about what's called a modified Atwood machine, which kind of takes it up a slight notch above. But for the most part, it still ends up being the same method. That's one thing that I want to point out is when I set up the Atwood machine, you want to take note of the setup for it, because this setup can be used for every single multi-mass setup and for every single Atwood machine, modified Atwood machine, regardless of how complex it becomes. The method stays the same. So we're going to basically set up the same way that we did before. In the original case, if we want to find the acceleration, what we did was we treated it as a system where we looked at one complete object. In it, we know that the acceleration is still based off of the equation F net equals ma. Now, once again, because we have two objects that are moving because of the net force, I need to make sure that I note that the mass is the sum of these two masses because both of them are moving. So that's one thing to note when you're using this equation, F net equals ma. You're putting in the mass that's moving in the frame that you're looking at. If you're looking at it as a system, as one complete object, then you have to include every single mass that is moving in the system. If you're only looking at individual objects, like if you're just looking at M1 or just M2, then the M in here would just be the mass that you're looking at. So you want to make sure that the mass that goes into the F net equals ma is the mass that's moving in your reference, the field of view that you're doing. All right, now we have to actually talk about what is F net. Now this is where it becomes a little bit different from before. If you recall, the way that we did before, I mean, we kind of made it into one complete object, but I did show briefly how you can set it up for two separate FBDs. In it, we would make an FBD for the two scenarios, and then we would just look at every force that was going in the direction of the acceleration, which happened to be all the horizontal forces, and we made positive and negative based off of the direction. We're going to do the same thing here, but the pulley kind of changes things a little bit. So let's start off with the FBD. Mass 1 and mass 2 both have a force of gravity pulling down, and they both have a tension force pulling up. That's easy enough. So the FBDs are going to look like this. One thing to note though is that we know that since the mass 2 is heavier, it's going to accelerate downward. Now, I didn't do it in this FBD, but one thing I would highly recommend is that you include at the very side the direction of the acceleration of the two blocks. So we know that mass 2 is going to fall down, and because they're connected by this string, since mass 2 goes down, mass 1 should be accelerating upwards. Now this is where it becomes important. Now that I have the forces acting on the objects, I'm going to look at every single force on both of these objects that are acting in the plane of the acceleration. So since this acceleration is vertical and this acceleration is vertical, I'm going to look at every vertical force on the two objects and add them together in order to find the net force. I don't think I wrote it out here, but when we do this, I look at M2. It has a force due to gravity pulling downward. The acceleration on M2 is also down. So this ends up being a positive M2G acting on this block. Now there's a tension force pulling up. Now normally in typical problems we make up as positive, down as negative, but we're going to define positive as the direction of acceleration. So because this was going in the same direction, I made it positive. Tension in this case is now going to be negative. So we're going to have M2G minus T. Now I'm going to go to the second object. Here, acceleration is now different. It's actually going up this time. So this tension becomes positive T. And then down here, we have the force due to gravity pulling down, which makes this negative M1G. Notice that I can now simplify this a little bit, and I have minus T plus T. Both these tensions are the same, so now that drops out. This acts exactly the same way as the previous multi-mass setup, where the contact forces, the interactive forces between the two blocks, dropped out. And that's one of the fundamental aspects when you're looking at the object as a system. You're looking at it, everything all together. Those interactive forces are supposed to drop out. If you can treat this setup as a system, where it's treated as a single object, let's say, that means that the interactive forces don't matter. They cancel out. If they don't cancel out, that means it's technically not that type of scenario. It's a little bit more complex than that. So just keep that in mind. Now, if I wanted to do a similar setup that I did before, where I kind of make it all into one big block, if you recall, I did that for the scenario where I had a 3 kilogram block and a 5 kilogram block touching like this, and I just made it into one big 8 kilogram block. I could do something very similar to here. The one thing though is that I have to note that the pulley changes what is positive. The positive for M1 is different than the positive for M2. So I need to make sure that when I put these next to each other, or in this case on top of each other, I want to make sure their accelerations are pointed in the same direction. So since M2 is pointed downward, I need to make sure that M1, which is initially pointed upwards, is flipped upside down so that it also points downward in the same direction. So that's kind of what this ends up looking like if I combine it. And now we can see that M2G and M1G are in opposite directions, which is what we get here, that the net force is actually the difference in these two weights. All right, so let me actually clear this out. All right, so I want to show that work a little bit because it is really important that you know how to set this up. And like I said, if you can master this aspect of drawing the FBDs, drawing the accelerations, going through all the forces in the plane of acceleration, and making things positive and making things negative, then the problems will become significantly easier. And no matter how crazy I get with these Atwood machines or modified Atwood machines, you'll still be able to tackle them. All right, now these are the two equations we have. We had the net force, looking at the sum of the forces, which just ended up simplifying as the difference in the weights. And then we end up having that the net force is equal to the sum of the mass times their combined acceleration. Bringing it together, I could set them equal to each other because F net is the same. And we end up getting this equation. So this is a general, this is what we would call a derived equation for an Atwood machine. This means that this equation works for any pure Atwood machine where the pulley is frictionless and where M1 and M2 are the only masses. If there is any other change in the setup, I can't use this. So for the next few problems, you can get away with using this equation. However, I would highly recommend that you practice setting it up just like I did here. Because if you can set it up here for this type of machine, like I said, it's practice for the future. If you just memorize the equation, this derived equation, as I said, this only works for one specific setup in a pure Atwood machine with a frictionless pulley and two masses. If I change that scenario any bit, maybe I make the rope massive, maybe I make the pulley massive, maybe I include friction, maybe I change where the masses are located, I add in a third mass, this equation doesn't work anymore. And if you don't know how to derive it, then you'll be out of luck on the test. So I highly recommend that you practice now with the setting up. That way in the future, regardless of how crazy an Atwood machine becomes, you know how to set it up. All right. So again, we end up doing the exact same thing. If we want the acceleration, we look at it together. If I want to find the tension, then I want to look at each one individually. And again, the big trick is to remember that the acceleration points in the direction of positive. That's the main kicker. All right. So working this problem, pause the video, work itself. I'll go over a second. All right. So in the first part, I want to draw an FBD for this. So little mass has a force going down and a tension force going up, and it's accelerating upwards. The big mass has a force due to gravity going down and a tension force going up, and it has an acceleration going downwards. So what I can do is, this is how I would derive it. I'd start with F net equals ma. Remember, we always have to start with one of those basic general equations. Going through the forces, this is in the direction of my acceleration. So this is going to be positive, minus the tension force because it goes opposite, plus this tension force because it's in the same direction of acceleration, minus this force of gravity. The tension forces are going to drop out, so that's going to leave me with this, which is 50, minus this 20, and then the mass is the combined mass of the two moving objects, 7. So I end up getting 30 divided by 7, which is 4.29 meters per second squared. For part B, I need to find the net force on both of these objects. Now, it's not asking for the net force on the system. We already know what the net force on the system is. We found it up here. What I care about is the net force individually. So for the big mass, we just do F net equals ma. We do 5 kilograms times the 4.29, and we end up getting that the net force is 21.45 newtons down. For the little mass, we do the same thing. We just change the mass to 2, and we end up getting 8.58 newtons, this time going upwards. Notice how these net forces are matching direction with the acceleration, because net force always points in the same direction as the acceleration. All right. Part C, they want to find the tension forces. So I pretty much do the same thing. This time I'm looking at the net force not as equal to ma, but as the other equation being the sum of the forces. So for the big mass, this is the positive, so Fg2 minus the tension force. Plugging my numbers in, I end up getting that the tension is 28.55 newtons up. Technically, the tension forces are the same, so I shouldn't have to do the little mass, but I'm going to do it anyway as a good check. So I plug my numbers in. Again, this time, the tension force is in the direction of acceleration, so that one's the positive one, minus FG1 going down. Plug the numbers in. This time I'm actually adding these two numbers, and I get 28.58. You'll notice that these two numbers are slightly different. That just comes down to rounding. If I didn't round my numbers as much as I did, these numbers would be a lot more precise. But for the most part, they're really close. They're, off by the fourth digit. So that's really not that bad. And they both round to the same third digit. So that would be pretty accurate. If there were any more off though, then I would have wanted to double check my work to make sure that I did my math correct. All right. Now work on question 30. Pause the video, work itself, and we'll go over in a second. Okay. So once again, I'm pretty much going through the same setup, so I'm not going to go into too much detail with this. Once again, we start off with drawing our FBDs, making sure to include the direction of acceleration. We do the same setup, F net equals ma. We're pretty much always doing F net equals ma. We again go through all the forces, and nothing really changes, just the numbers. So we end up getting this time 80 minus 50 equals 13a. So my acceleration ends up being 2.31 meters per second squared. Again, same thing for part B. We'll plug in F net equals ma, plug in the numbers, and we get that the net force on the big mass is 18.48 newtons down, and for the little mass ends up being 11.55 newtons up. All right. Part C, again, same setup. We're doing F net equals we're looking at F net equals the sum of the forces. So for the big mass, it ends up being the difference, with Fg being the positive. Plug the numbers in, and we end up getting this one has a tension of 61.52 newtons up. Do the same thing for the little mass. Again, technically we don't have to, but we end up finding that we get the same results. Again, it's the fourth digit that's slightly off. Nothing too crazy. This is close enough to say that that's probably the correct answer. Now, one thing I'll point out is, because of the fact that the tension, the interactive forces are always the same, I always recommend that if you're going to answer the problem, choose the scenario that has the simplest FBD. You'll see what I mean about that in a second, but for the most part, or not now, but in the next video, but for the most part, whichever one has the least forces is typically the better choice to choose, because it doesn't really matter which tension I'm looking at. They're both the same. All right. So this is the last question. So pause the video, work itself, and we'll go in a second. All right. So they want us to rank the following scenarios by greatest acceleration. Now, first thing I want to do is I want to find the accelerations for each one. I'm not going to go into too much detail. Again, you can see what I did in the previous problems. What I'm actually going to do for this is, because it's such a generic Atwood machine, I'm actually going to use the simple derived equation on how to find the acceleration. So for A, I end up getting this. It's going to be 2/3 of g, or 6.67. There is a unit. I'm just dropping the unit for now, but this is meters per second squared. Now you'll notice this CCW. This stands for counterclockwise. Since 5 is the bigger mass, the pulley is going to go this way. So it's going to go, this one is the one that's going down, and the pulley is going to end up pulling, rotating counterclockwise. I'm going to do it for all of this. So B ends up being half G, or 5 meters per second squared counterclockwise. This one's going to be 1/3, or 3.33. D, because it's actually the right one that's heavier, this ends up being 6 clockwise. E and F. So these are all the accelerations. Now, there's a few ways that you can answer 31 because it's not really specific enough. Now, on the one hand, it says that it wants the greatest acceleration. As we know, acceleration is a vector. So that means that technically there's a positive acceleration and a negative acceleration. Now, depending on who you talk to and the scenario, that could make one acceleration greater than another. So negative 10 can be less than positive 10 to some people. Um, if you do that, then what you would get is either ranking them as A is greater than F, greater than B, greater than C, greater than E, greater than D, or you can have them flipped. Um, Normally, if that was going to be a case, they would have to define a certain direction as positive. Conventionally, this is something that you're going to learn in the rotation section. Counterclockwise is usually defined as positive, and clockwise is defined as negative. So these would be positive numbers. These two, D and E, would be negative numbers. So essentially, what I'm doing here, this is considered positive 6.67. This is positive 6, positive 5, positive 3.33, negative 3.3, and negative 6. That's why it's ranked like this. If they define clockwise as positive, then all you do is flip these arrows around. Uh, that's one, or I guess technically two different answers that you could have. Or if you're ranking this based off of the magnitude of the acceleration, absolute value where we're not taking into account signs, then we end up having this. A is still the largest, but now D and F are both have a magnitude of 6, so they would be ranked equally. And similarly, C and E are also equally ranked, so they would have an equal sign because their magnitudes are the same, and we could get this. So this really depends on on how you read this. I would, if I was going to ask this on any test, I'd have to be a lot more specific of whether or not I was looking for the magnitude only, or if I wanted you to also include direction. So, including direction. But if I did this, I would have to define positive. So I would have to define either counterclockwise as being positive, or I could define clockwise as being positive. So if you got either of those three answers, I would count that as a win as long as you understood why you got to that. And that's pretty much it for the Atwood machine. Now, there is going to be one more video after this about multi-mass systems where we're going to talk about what's called the modified Atwood machine. Those are a little bit more fun. They're ones that I can go a little bit more crazy with and make them a little bit tougher. But the nice thing about them is that as long as you apply the same exact procedure that you did for that regular Atwood machine, uh, the problem doesn't become that much more difficult. It just becomes a little bit longer. Now, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.